language is what connects and divides humanity at the same time, right? And to connect those who do not speak 40 or more languages fluently, we need smart tools. No surprise that AI comes in hand here as well. Dr. Jurgita Kapociute-Dzikiene is about to reveal if artificial intelligence is able to cross barriers between languages, and could it be the salvation for smaller ones. Dr. Jurgita is a language technology specialist at Conferene IT and a full professor at Vytautas Magnus University. She has been working in the field of AI since 2005, and her main research focus for the last 10 years is on language technologies. Good day, Jurgita.
Good afternoon.
All right. Yes, good afternoon and good morning to everyone, because we do have an international conference today. So we may be having people connecting from Sydney to Australia to New York.
That's nice.
Where are you connecting with us from?
From Kaunas, from Lithuania.
Amazing. Jurgita, my main question to you before you start is, are you afraid of AI?
No, of course, definitely not. I'm a friend with it, so for quite a long time.
Amazing. So, Jurgita, the virtual stage is yours.
Thank you very much. Before I start, I want to say that various natural language processing problems today can effectively be solved only if you have enough amounts of the training data. Then, of course, you can train the neural network model and later use it for the future predictions. So if you have some training data in the specific language, you can train the monolingual model. And if you have the data for several languages, you can train multilingual models. And I would say the most famous models of today are BERT model, which is the language model, and its multilingual version supports 104 languages. And it can be later tuned for various tasks: sentiment analysis, intent detection, and other classification tasks. Another famous model is GPT-3. It's already generative model. It supports all digitalized languages. And it is already fine-tuned for the specific tasks. So here I'm talking about multilingual solutions. But you know, it is still very unnatural for us humans, let's say, because if we read something in one language, we can transfer that knowledge and use when speaking in another language. So here I'm talking about some knowledge sharing between different languages. And here I'm talking about cross-lingual solutions where different languages could benefit from each other. But before I speak about Tilde's projects and about this topic, I just want to say that today Tilde has about 14 ongoing international projects. But I'm going to talk about the research done in 2 of them. So Comprise project and Stairway to AI project. And of course, there are a lot of challenges from the research perspective there, but I would focus on 2 problems. So in the Comprise project, we are trying to create the chatbot that could understand questions in different languages. So this is the intent detection problem, when the class of the question is identified and then the answer is prompted. But as I said, we want our chatbot to deal with different languages. And in Stairway to AI project, we are dealing with the classification task as well, but we are dealing with extremely small data sets. And it seems that we are kind of going the opposite direction everybody are going today, because with the neural networks, you need big data. But you know, customers usually want us to do miracles with the small data, not with the big data. So Let's look a little bit deeper into what was done in this project. So the motivation behind of it, that we want to make the dialogue systems available for different languages. And we face the problem because some training data do not exist in different languages, or if the data set exists, it is proprietary. And even more, we want parallel data here to compare the results. So one of the possible directions could be to use the existing data set, but machine translate it into our target languages, because, you know, machine translation tools are quite accurate today, especially dealing with normative texts. Or another, much more innovative solutions to find some cross-lingual solutions that could work for many languages. So right now about the data set. As the good example of it, we use the data set which was originally in the English language, and this data set is about the tildes biuras prices, licenses, technologies, vocabularies. So its training split was machine translated into German, French, Lithuanian, Latvian, and Portuguese. But its testing split was manually translated into the same languages. And the idea behind of it is that if you do not have the data, the training data in the target language you need, maybe you can borrow the data from another language and machine translate it into your language and train the model. But the real users are already going to ask questions in their own language. So in German, French, Lithuanian, Latvian, and Portuguese. So in this data set contains 41 intent, so 41 class. And as you can see, the data set is not very big. But as you already heard from me, users want us to make miracles with the small data, not unfortunately with the very big data. So this is the classification task, right? But the text cannot feed into the classifier directly. So we need intermediate stage, and vectorization performs it. So we need, first of all, to convert all these texts into the numeric format, because neural networks, as the classifiers, they can deal only with numbers. And for the vectorization, we've chosen two approaches. The first approach is to vectorize each word in the text and then concatenate those vectors into the huge longer vector representing the whole text. As you can see, this type binds to the specific order in the sentence, right? And it is not very suitable for languages as, for example, Lithuanian, that has relatively free word order. But for some languages, it works perfectly. So, but if you concatenate word embeddings, you can still retain boundaries between words, and you can search for the specific patterns there. So with this vectorization technique, we have tested 6 BERT word-based embedding models. So 4 of them were monolingual for the English language. As we know, English language has a lot of different pre-trained models, and 2 of them were multilingual, supporting our all target languages. And another direction is to vectorize the whole text at once. So from this perspective, the semantical meaning is retained of the sentence, of the text as the whole. And with this vectorization technique, we used 8 sentence transformer models, BERT-based transformer models. So since we already know how to vectorize texts, how to convert them into the numeric format, you can see that when we already have and we know the dimensions, so in the illustration you can see only 2 axes, so 2 dimensions, but in the real cases we've used the BERT embeddings, so they are 760, they have 768 dimensions. So, but still classification can be done in different way. So we experimented with a discriminative based. So first of all, the classes of different instances were identified during training stage. And after we know the boundaries of these classes, it is very easy to attach the new incoming unknown testing instance to the specific class. So with this, we've tested convolutional neural networks, BERT fine-tuning, and feed-forward neural network as dense layer on the top of sentence embeddings. And this is another approach. This is the memory-based approach where the instances, again, placed into n-dimensional space. But this, since this is the memory-based approach, there is no training, simply the storing of the training instances. And when the new unknown instance arrives, the distances between different examples are calculated. And this new instance is attached to the class to which is the closer. As I said, we've used cosine similarity here. On the summary, we've tested BERT and word embeddings and BERT sentence embeddings with a convolutional neural networks, BERT fine-tuning, dense layer on the top, and cosine similarity as the memory-based approach. But next to various approaches, we've also tested different training and testing strategies. Under monolingual strategy, the training and testing was done on absolutely the same language. Training on German, testing on German. With a multilingual approach, the training was done on the target language, plus together with on the English language. So but the testing was done only on the target language, but still the training model saw the examples of the target language. But I would say the most interesting thing is going on here, because with the first cross-lingual strategy, we've trained on the English language only, but tested on some other unseen language. So in this case, the model, the training model, haven't seen any example in the target language. And with the second cross-lingual strategy, we've trained on several languages at the same time, but not the target one, but tested on some other unseen target language. And during our experiments, we evaluated the accuracy, and you will see the results averaged in 5 runs, except for the memory-based approach, because each time there is no randomness, each time it gave the same results. And it is also very important to calculate baselines. Well, you see, our data set was not very balanced, but there are the calculated baselines, and they are very, very low. Usually, the method must exceed baselines to be worth something. And in our case, the baselines, according to the data set, are really very low. And they are exceeded. So there are the results for different languages with the different approaches. But let's, for the first, look at the top line. So this result, 84% of the accuracy was achieved with the English original data set and the monolingual model. So it means that the training and testing was done on the English language. And you know, when performing experiments in different languages, we intentionally, or sometimes not intentionally, but we compare our results to what is achieved for the English language. So in this case, we also compare it, what is achieved with the English language. So the highest as we can get with the English monolingual model, as I said, was 84%. And in red columns, you can see monolingual results obtained for various languages with a machine translation, for the German language, for French, Lithuanian, Latvian, and Portuguese. And the results vary from 4 up to 8%. So the gradation is even up to 8%, and it very much depends on the language. So let's look into the multilingual results, and they are much higher. They are, I would say, quite close to our top line. So I just want to remind you that in this case, models sort the instances of the target language and also of the original English language. And the results are, as I said, quite close to the top line. But much more interesting to see how cross-lingual performs. And you see that the first cross-lingual approach, the results are quite close to the monolingual results. Actually, they are not, the differences are not statistically significant. So with the clever transformer model, we can achieve almost the same accuracy as translating the data into our target language we want. But even more interesting thing is going on with the second cross-lingual approach, because here we went very close to our top line, and for the Lithuanian language, the top line is even beaten. Well, the result above, it's not huge, but still, the cross-lingual model was able to cross this boundary. So, right now, let's move to another solving task. And here, as I said, we are dealing with the extremely small data sets. And we have the data set in the English language. This is labeled data set, but we have only a few instances in each class. So this is the very, very challenging text classification task. So two possible directions here. One direction, of course, is to augment the data set at any cost by adding synthetic samples, for example. And another idea, since we are dealing with the English language, maybe to offer solutions that almost do not require training data. But let's look to the data augmentation. So for the data augmentation, we've tested and we used paraphrasing, back translation, and summarization. So paraphrasing and summarization was done with a T5 transformer model, and back translation with the Google machine translation engine with the Lithuanian as the intermediate language. And you may ask, why Lithuanian? Why not other language? And explanation is not because I'm Lithuanian, because the machine translation into, for example, German language and backwards gave almost the same instance. So there is no use to duplicate instances that we already have and to cheat. So this is the reason why we were using Lithuanian. And here you can see two data sets. The original one, as I've said, it is very small one, and we have two classes, planning and scheduling, and only 40 instances, that's it. In the augmented data set, we have more instances, 160, but it's still very, very small data set. And there are the solutions we used. So the first solution was zero-shot learning with the birth sentence embeddings. What zero-shot learning does? First of all, you need to give the class labels, so planning and scheduling, and based on these labels, the zero-shot pre-trained model is able to identify kind of boundaries of these classes. And when those boundaries are already identified, the instances can be attached to the specific class. Another approach, this is, by the way, memory-based approach, the same one that I was telling you before, but in this case, instead of the training instances, we have profiles. And these are Wikipedia from the Wikipedia taken definitions, what the planning means and what the scheduling means. And here we make the assumption that the instances that describe, for example, planning from the semantical point of view will be closer to the definition of planning. And for the scheduling, vice versa. And here you already saw the discriminative-based approach, and for this we've used sentence, bird sentence embeddings with the dense layer on the top of it. That was tuned. During our experiments, we evaluated the accuracy, but we performed five-fold cross-validation with the classification approach because we're dealing with a very small data set. And you see random and majority baselines. Since the data set is balanced, our baseline is 0.5, and we must go above. And we really went above. Not much with some approaches, but still. In red, you can see the results achieved with the original data set. And in green, you can see the results with the augmented data set. And you may ask me why we do not have the results for the classification approach. But we augmented our data set. We added synthetic instances that still do not assure enough variety there. They are still the clones of the previous instances. So if we would perform the training and testing, we would kind of cheat here. We would get closer to 100%, but it will tell us nothing here. So you see that the best results were achieved with the classifier, with the BERT sentence embeddings and feed-forward neural network, and the original data set. But what I want to say here, the differences between various results are not statistically significant. So what does it mean? It means that our data set is too small to make the conclusions, so which method is the best? So all it demonstrates that if there is not enough amounts of the annotated data set in some, at least in some language, it is very difficult to offer the good solution. But if the data set exists in some language, it can be used for the other languages. So the other languages can benefit from it. And we even don't need the machine translation. So in this case, I would conclude that the boundaries between languages can be crossed. So thank you very much for listening, and I'm looking forward to your questions if you have.
Thank you so much, Jurgita. Thank you so much for a really interesting keynote presentation. Yes, we do have a few questions. The first one would be, had the COVID-19 pandemic any impact in kicking the multilingual solutions for public services?
Well, I think the life is going on. I think nothing stops here. And I would say sometimes we even see the larger progress due to it. You know, everybody is sitting at their computers and have to do something. Of course, this is, the way to experiment, to do the research and so on. So I would say that the life is going on and there is quite a lot of progress recently, and we will still see it.
Amazing, thank you for that. And Doctor, one more question from my personal side. In very human language, when can I expect my mom to have a chance to easily travel to, let's say, Argentina and be able to speak freely and use the AI-based solutions in order to communicate with people?
Yes, I guess your mom is Lithuanian, right?
Absolutely.
Yes, it is difficult question, I would say. I don't say that the progress stops, but you know, the user needs are growing each day and we want the same quality as the English speakers have. We are working on that. And I don't say that today your mom cannot use the available tools, but probably they are still not the quality she wants. So the researchers in Lithuania, different companies and universities are working in this way to make your mom to understand and to talk with others through apps in Argentina.
Amazing. Thank you so much, Dr. Jurgita, for your answers. Ladies and gentlemen, that was Jurgita Kapociute-Dzikiene, professor at Vytautas Magnus University and IT researcher at Tilde IT. Thank you for that.
Thank you very much. It was a pleasure to be here.